Okay, now we're going to talk about Euler's formula and movement in the Argand plane. So, the exponential form of a complex number uh, can be written like this. E to the I theta is equal to cosine theta plus I sine theta, and that's known as Euler's form. So, basically, when we had our rectangular form, a plus bi, for our complex number, we also learned we could write it like this, where we have our modulus times cosine theta plus our modulus times sine theta, and we factored this out, and we were writing this as r cis theta. You might recall that from our um, earlier assignment, that r cosine theta, r sine theta can be written as r cis theta. And if I'm going to write it in Euler's form, I could write this, instead of writing it cis theta, I can write this as e to the I theta. Okay, so as I mentioned, you should have had a bunch of practice doing H8F.1, which talks about converting uh, to actually, I don't know if this talked about converting, but this talked about how to multiply, divide, and do powers of when operations with complex numbers. Okay, so super important that you do HF.1. Okay, so but the first page here is about just Cartesian. So I'm sorry, just adding and subtracting complex numbers. So as we learned here, you're only going to do adding and subtracting of complex numbers in Cartesian form. What do? We're going to add the like terms, and so if I had these two things I was adding, I'd have 1 plus 2, which gave me 3, and then I add the radical 3 plus 2i, which gives me the imaginary part. Okay, so same thing here. I have 1 plus 3i and 4 plus I. So this is z1, and this right here is z2. And if I add these together, I'm going to get 1 plus 4, which is going to give me 5, and 3i plus I is going to give me 4i. And so I can plot this here, z1 plus z2. And what happens if I join O to z1 to z1 plus z2 and z2? If I join everything together, notice here I'm going to get a parallelogram. Okay. This has the same magnitude. This line here, this pink one here, has the same magnitude. If those are the same and those are the same, we have a parallelogram. Okay, so what conclusion can you reach with a geometrical interpretation of additional complex numbers? So adding complex numbers is sort of like adding vectors. Okay, and then subtraction can work the same way. Subtracting is like changing the direction of the vector. So I've got z2 is this one here, right? 4 plus I, right? And if I'm subtracting z1, I'm going to go this. If I've got z1 minus z2, instead of going that direction, I'm going to go this direction. And z1, we're going that direction. So so this one didn't change direction. It was a z2 changed direction when I did minus z2. Okay, so it's also like making a parallelogram and sliding the vectors around. So conceptual question, how is addition and subtraction of complex numbers compared to addition and subtraction of vectors? And they work the same. Okay. Now, multiplying is a little different. So if I've got z1 is 1 plus 3i, and if I've got z2 is I, so here we have z1 equals 1 plus 3i, and z2 is I. So if I multiply those together, 1 times I is going to give me I, 3i times I is going to give me 3i squared, and I squared is going to be negative 1, so negative 1 times 3 is going to give me negative 3. Okay, so I can plot this down. So we've got z1 is 1 plus 3i, right? z1 is 1 plus 3i. Right? Go over 1, up 3. z2 is I, so I'll just plot that right there. Right? It just goes up 1. And when I multiply those together, we got, let's use another color. We got negative 3 plus I. So we go negative 3 plus I. So notice the modulus of this is the same. The length of the pink line and the orange line is the same. When I multiplied by I, it added pi over 2. So the argument increased by pi over 2. It looks like a right angle, doesn't it? And the modulus stayed the same. Now, this says repeat by multiplying with 2i. So guess what? If you multiply by 2i, then the modulus will be doubled. Right, so if I multiplied by 2i, then this line here would be twice as long. Okay. All right, so the definition of e to the I theta is this. So show that the modulus of this is equal to 1. So if I've got the modulus of this, and I know that e to the I theta is equal to this, all this stuff here, right? Okay, so to find the modulus, you take each thing squared. So if I have cosine squared plus I sine squared, then we know from our unit circle that cosine squared plus sine squared is equal to 1. And is that formula in here? Should be. Yep. Okay. So it's important. You don't have to memorize this. You can just remember that cosine squared theta plus sine squared theta is equal to 1, and hence we've just shown this. And you might remember that from the unit circle when you've the radius of this is always going to be 1. Okay. So state the modulus and argument I, and hence write I in the form r e I squared, or I theta. So if z1, we've got a modulus of 1, and we've got our angle, our argument, is pi over 2. So if I know my argument is pi over 2, and if I know my modulus is 1, if I'm going to write this in And if I'm going to write this in the other form, in polar form, then if I'm going to write this in Euler form, my modulus is, we just said 1, and the angle is pi over 2. So I can rewrite this as 1 times e to the pi over 2. Okay, very important that you do this H8E.1 revision village and the other one as well. Okay. All right. So I times e to the I pi. We just said that we can substitute I with r e I to the power of I theta. So if I'm going to substitute this with e to the I pi, we can get we can add these arguments together. Because when you have a power, something to a power times something to a power, you add the powers together to simplify. Okay. So the most important thing from this lesson, and you did this in this assignment here with Revision Village, is when you're in Euler form, when you're multiplying two complex numbers together, you're going to be multiplying the moduli together, and you're going to be adding the angles together. Okay. And if you're dividing two imaginary numbers together, then you divide the moduli together and you subtract the arguments. Okay. And if you're doing an argument to a power, if you're multiplying a complex number to a particular power, you put the moduli to that power and you multiply that power times the argument. Super important. Okay, so I just wrote those formulas here that we did in the Revision Village H8F.1. Okay, so this just says what I just said. Multiplying complex numbers by other complex numbers causes the magnitude to increase and the arguments to rotate. Okay, so so 3i times radical 2 and 3i times radical 2i is going to give me this, right? And we know that I squared is -1, so this is going to change to minus 3 radical 2. And then we've got that there. And if I plug this into a calculator, I get this. Okay, because square root of 2 is about 1.41. So show all of these on the Argand diagram. So, okay, so radical 2 plus radical 2i gives me this one here. Okay, 3i is this one here, and when I multiplied those together, we ended up with negative 4.24, and then I went up 4.24i. And then notice how the length of this pink line should be 3 times as long as the yellow one. Because of this 3, we made the modulus 3 times longer when we multiplied. And once again, we went around, because we multiplied by I, the argument increased by pi over 2. Okay. Now we want to write this in exponential form. So first thing we did was we find the modulus. how do we find the modulus? We know that in the x direction we're going square root of 2, in the y direction we're going square root of 2. We square that, and we square that, and we add those together. We get square root of 4, and we get 2 for our modulus. Okay, our angle, if I go over square root of 2 and up square root of 2, we've created a 45-degree angle, and if I've got a 45-degree angle when this and that are the same, then our angle in radians is pi over 4. So if I know my argument is pi over 4, and if I know my modulus is 2, I can put it into Euler's formula, which is just like this. I can replace the modulus with 2 and replace the argument with pi over 4. Okay. Okay. So what is the exponential form of a complex number? So the exponential form is also known as Euler's form. Okay, and it's written in this form. Okay, and geometric of multiplying, the geometric effect of multiplying two complex numbers ends up with, when you multiply two complex numbers, we're ending up multiplying the moduli together and adding the argument together. Okay, that's the main concept. And then if I've got complex numbers to a particular power, same sort of thing. You're going to have the moduli put to that power, and that power you're going to multiply times the argument, and this will make the angle get bigger based on whatever the power is. And it's going to increase and rotate counterclockwise. Okay. Give it that tan pi over 6 equals 1 over square root 3. Find the modulus and the argument of negative square root of 3 minus I. Okay, so the first thing I do, we drew the picture here for you. So negative radical 3 goes down to here, right? Negative radical 3. And then negative I, we're going to go down 1. And so that puts us here at negative radical 3 minus I. So first of all, if I want to find the modulus, I can take this x direction, negative radical 3, and square it. And I can take the y direction, which is negative 1, and square it. And I end up with 3 plus 1, which gives me the square root of 4, which gives me 2. So my modulus is 2. Okay. My angle can be found when I notice the opposite side is 1 and the adjacent side is negative 3. So we write our tangent opposite over adjacent, so 1 divided by square root of 3. And so my angle is going to be pi over 6. Okay, because we know that 1 divided by square root of 3, they've already told you that that angle is going to give me pi over 6. Okay, now, but we're really looking for this angle here that I'm marking in blue, right? So to get this, I can go to negative pi and then subtract this. So if I go to negative pi and add pi over 6, that's going to take me to this spot on this line, which is going to give me 5 pi over 6. Okay, so I can say we have negative 5 pi over 6, or we could write it as 7 pi over 6, which means we go from here all the way over to here. The textbook likes to have our answers between pi and negative pi, so I would most likely use it this way. So now if I want to write this in exponential form, we know the modulus is 2, and we know our argument angle is negative pi over 6. Negative 5 pi over 6. Okay. So for the imaginary value of this to equal 0, the complex number needs to get multiplied by pi. So what if we're going to put this to a particular power, okay, and we want this to equal to 0, then we need to make this here equal to k pi. So in order to equal to k pi, because if you have this to a particular power, we're multiplying that number to our argument to figure out how much it's rotating. And if the imaginary part is going to be 0, basically what we're saying is it's going to be somewhere. There's going to be a real value, but if the imaginary part is going to be 0, it's going to be somewhere here on the x-axis, and we want this to be somewhere on the x-axis. So in order for somewhere on the x-axis, we have to either be at pi, or at or negative pi, or 2 pi, or 3 pi, or 4 pi, or something. We have to be at some value of pi. So to figure this out, if we multiply this to the 6th power, then we're going to get rid of the 6 in the denominator. And then so I end up having z to the 6 times 2 to the 6 times e to the I, and then the pi over 6 times 6 is going to give me negative 5 pi. Okay, and so so I end up with 2 to the 6, and so remember, we just said this is going to give me an imaginary value of 0. So this is going to be e to the 0, and anything to the 0 is going to give me 1. But this is I, so we're going to have negative 1 here, and so we end up with negative 64. Okay. Okay, investigation 7. So if I've got a function like this, z equals 2e to the t I, okay, this is going to form a circle. The modulus is not changing, but the angle will continue to increase as we twirl around. So basically what this here has is we've got, it just makes a circle where the radius is always 2. But the angle will keep changing. Our argument, the argument will keep on changing. But what if I've got the modulus is changing and the argument is changing? So here, for t, as t increases, the modulus is going to get bigger in this, with that being the case. And up here, as t increases, the argument's going to get bigger too. And by that when that happens, you're going to end up with a spiral that keeps getting bigger. So the modulus keeps getting bigger, as you can see. The orange lines keep getting bigger and bigger and bigger, and the angles keep increasing because we're multiplying our complex numbers together, so that's making the argument bigger, which is causing the result to rotate. Okay, so we will practice with suitable software in a Desmos activity. Okay, and so how can complex numbers be used to create spirals? So a complex number in which both the argument and the modulus are written as functions can create curves. Okay, so now we're going to try to do the first part here. together. Okay, so um, maybe I'll do this in a separate video. I think I will.